This video is going to be about logistic models, specifically logistic differential equations, which falls under the subcategory of differential equations in AP Calc BC. This is a BC only topic because while in AB you do learn about exponential models, growth and decay, you're not going to learn about logistic models. We should know about the exponential model, which is just dp dt is equal to kp. And if you were to solve for this using separation of variables, you're going to get e to the power of kt, just like how you would get in a normal exponential model. But logistic models model the real world a bit better. Exponential models just mean it keeps on going up and up. But sometimes there's a cutoff point. Sometimes a population cannot grow farther than this point. Sometimes the disease cannot spread to more than this many people. And so you want to sort of mimic that. You want to slow down the rate as it approaches this point and not go over it. Sometimes it can go over it a bit, but once it does, the rate is negative, and so it oscillates back and forth until it's basically that value. And this value is m, the carrying capacity. And so the logistic model we'll be looking at takes this carrying capacity into account. Simply put, it's dp over dt is equal to kp, just like the exponential model, but we also have to add this term 1 minus p over m. Sometimes you write it as m minus p. It's very similar. I'm just going to use this because this is what most textbooks and most classes use. How would you solve an equation for this? That's going to be the main thing. You would need to probably solve this in an FRQ. And the derivation of it isn't too bad. It's just going to be separation of variables. This is a separable differential equation. And so what we're going to do is we're going to move the p's to one side and the t's to the other. There are no t's here. We're just going to move the dt to that side. And so we're going to start with this. All the p's here, we're going to move to that side. So it'll be 1 over p times 1 minus p over m dp is equal to k dt. We take the integral of both sides. Okay. That is our initial setup, but we want to simplify this a bit so it makes it easier to integrate. First, we can multiply the top and bottom by m, and we get m over p times m minus p. That looks a lot better, no fractions, but we can also take this one step further and do integration by partial fractions. You should be able to do this, and so in order to not take away too much time, I'm just going to show you how to do it. It's 1 over p plus 1 over m minus p. I'm not going to show the steps of integration by partial fractions. That's for another lesson. But this, you should be able to derive knowing integration by partial fractions. You would just show the steps on the actual AP test, but I'm just going to jump to the partial fraction decomposition without showing the steps in this video. Okay, and now we have that. We can take the integral of it. Integral of 1 over p plus 1 over m minus p dp is equal to integral of k dt. This side is easy. It's just going to be kt, and then that plus c. We're going to say it's c2 on this side and c1 on this side. And how would we take the integral of this? Well, we just split into 2 and take the integral of each part. It's ln of p, and then it's actually going to be minus here because of this negative in front of the p. Using the anti-chain rule, this becomes minus ln of n minus p. And using properties of logarithm, this just becomes ln of p over m minus p. And then that plus c1 is equal to kt plus c2. We can combine the constants into 1, making it just plus c. And now moving back up here, we have ln of p over m minus p is equal to kt plus c. That's just the single constant we combined into. We take e to the power of both sides, and that becomes p over m minus p here is equal to e to the power of kt plus c, but that can be rewritten as e to the power of kt times e to the power of c because of properties of exponents. E to the power of c is a constant by itself. We're going to denote that as a, so it's going to be a e to the power of kt. Now is just simple algebra. We multiply both sides by the denominator a e to the power of kt times m minus a e to the power of kt times p, distributive property. Moving all the p's to one side, we have p plus a e to the power of kt. P is equal to a e to the power of kt m. Factoring, we get p1 plus a e to the power of kt is equal to a e to the power of kt m. And so p is equal to a e to the power of kt m over 1 plus a e to the power of kt. That is technically an equation, but if you want to simplify it further, we only want one of these values, a e to the power of kt. You can just multiply the numerator and denominator by 1 over a e to the power of kt to cancel that off. And that gets it out of the numerator. We get just m up here. Here, this becomes 1 over a e to the power of kt, which is just a e to the power of negative kt. And this becomes just 1. And so that is going to be our equation. P equals m over a e to the power of kt plus 1, or you can switch the order in the denominator, which one you prefer. And that's going to be the equation. There's a few constants here, though. K was a constant from our original differential equation, as was m, so we don't need to worry about that. But a is something new. And you can use a little bit of algebra, find out that a is just equal to m minus the initial population over the initial population. Again, you can figure that out by plugging in 0 into this equation and solving for it. If you plug in 0, you get the initial population here, and so you just get a equals this value in terms of the initial population and the carrying capacity. And so that is the equation of the logistic model and how to derive it. There's just one more thing left to do, and that is show you the slope field of the logistic model. And so this is a common question. It gives you an equation and asks you to draw the slope field. The slope field is pretty simple. It's going to be basically 0 slope at the x-axis because it's 0 there, and also at the carrying capacity, m. Because once it reaches that, there's basically no rate of change. It's just always approaching that. So it's kind of like an asymptote. Everywhere here, it's going to be slightly increasing first, then very increasing, then slightly increasing again. It's going to look like this. This is the point of maximum rate of change. And so it'll be kind of slightly increasing here, slightly increasing here. And that gives you sort of that curve shape we see over here. Up here, there's actually some values. It's just going to look like that. Because if it ever gets above the carrying capacity, it's always going to go back down to the carrying capacity, under it, and then kind of oscillating back and forth. And so if you were to draw a graph through this, it'll look something like that. Obviously not the best graph because this isn't a very accurate slope field. There's going to be a lot more slopes in between. But that's just a rough estimate. That's how a slope field should look like. And yeah, that's logistic models. Now the two main, two main applications of this are with population and with diseases, because both of these usually follow logistic models. Okay, it's time for a practice problem to incorporate what we just learned about logistic models. So this one is a disease problem, one of the most common ones. And right off the bat, we say there are 200 students. That is going to be our carrying capacity, because when a disease occurs, it cannot infect more students than there are. And so the maximum is going to be 200. That's going to be our carrying capacity. Now, we have 2 points. On the first 0th day, technically, there are 2 students. That's the initial population. And on the 5th day, there are 12 students. So we know the equation is going to be P is equal to M over 1 plus AE to the power of negative KT. I'm not deriving it here because I just did in a little while ago. Now, also, you may notice I switched the 1 and AE to the power of negative KT. You can do it either way. This is just a more common way. I just did it that way while deriving. Okay, we also know that A is equal to M minus P naught over P naught. And so what can we do here? Well, we can actually solve for A because we know M is 200 and P naught is 2. So 200 minus 2 over 2, that's going to be 198 over 2, or 99. And so P is equal to 200 over 1 plus 99 99 e to the power of negative kt. And now we just have to solve for k. We get 12 is equal to 200 over 1 plus 99 e to the power of negative 5k, because we can plug in the point 5 comma 12. And so first, we have 1 plus 99 e to the power of negative 5k. We just do 200 divided by 12 to equal that. That's going to be 16.667 approximately. And so 99 e to the power of negative 5k is going to be that minus 1, or 15.667. Now we divide by 99. We get e to the power of negative 5k equals that divided by 99. That's 0.158. And now we take the natural logarithm of both sides. So negative 5k is equal to the natural logarithm of whatever we got before, 0.158. That's going to give us a negative answer as expected because we do not want a negative k, negative 1.844. And so k is going to be equal to that divided by 5, or that divided by negative 5 technically, which is going to be 0.3687, just add an extra decimal point. And so our model is going to be p is equal to 200 over 1 plus 99 e to the power of negative 0.3687 t. I'm going to extend that a bit, center the 200. That is going to be our model. That's the first part of the question. The second part is predict the number of infected students on day 10. We just plug in 10 into this equation. And so that's going to be 200 over, in parentheses, 1 plus 99 times e to the power of our negative k value times 10. And if you were to plug it into your calculator, you're going to get 57.484. It says, well, it's the number of students approximated. It's going to be about 57 students. That would be our answer. And yeah, that's it about logistic models and logistic differential equations. It is a pretty interesting part of the differential equations unit, not usually covered, and I feel like it's more interesting than the exponential model part. And yeah, that's it.